Hello. This is our first of really 3 parts to an electromagnetic wave lecture. We're starting with a first part, I guess, with which we'll discuss some perspective to help us understand what we're trying to perceive mentally. You can't really see an electromagnetic wave, but we're going to do our best. So this is the electromagnetic wave. It's really the culmination of all the electric and magnetic phenomena. And another really easy way to think about this is to call it light, of course. That's what you're used to calling it, but light is really an electromagnetic wave. It can also act as a particle. We call them photons, but we're not going to go there today. So the electromagnetic wave, I'm going to break into 3 lecture segments in a sense. Our first gives us a little perspective. And so the end goal of this is to have a diagrammatic representation of an electromagnetic wave. So we're going to look at a little perspective first. Now I've drawn some of the pictures for this lecture in advance just to save us some time. The first picture I drew is sitting on an XYZ coordinate system. So the normal XY coordinate system is what you're used to. And I've just added a third dimension. If X and Y are the plane of the paper or page or screen you're looking at, then Z would be coming out of that screen. And so that Z can be represented with a bar like so. And you can just going to have to kind of imagine that Z is going in and out of the page. And if you're ever drawing a right-handed 3-dimensional coordinate system, we know X cross Y gives us the Z direction. So I'm going to scroll down and we're going to look at what I have drawn, which is just a cube, or it should be a cube. I'm not a great artist, but there you have it. And that cube has bars going out of the page, or edges, and it has edges going vertically, and those are kind of in the XY plane. The horizontal edges are in the ZY plane. And I've put more vertical bars and kind of horizontal bars going into the page on the front and the top surface of this cube. And so the idea is that we're giving you a little 3-dimensional perspective here, where we have the vertical slats and the horizontal slats, and as you can see, they are oriented at 90 degrees from each other. In general, the red components are going vertically. Again, those are in the XY plane, and those vertical components are actually going to represent the electric component of our electromagnetic wave. So I'm going to write the red will represent the electric component, and I'm going to also put, I'm going to put that the blue will represent the magnetic component. And so you might note that they're always orthogonal or 90 degrees from each other, but you can see that in the picture ideally. Okay, so this gives us some perspective in general. Now what I want to do is actually show you a diagrammatic representation of an electromagnetic wave. And so down here I've drawn it already just to, again, save us some time. So we have an electromagnetic wave where we have 2 different components always working together, the red and the blue component. And as you can see, those should have a similar perspective to the cube that we just looked at. So we should have both red and blue components, and those are going in the direction shown by this vector here. It's called a pointing vector. Now, I did not misspell pointing. Pointing is the last name of a well-known physicist who came up with this. So the pointing vector gives us the direction of propagation of the electromagnetic wave, and the pointing vector can be represented mathematically like so. 1 over mu sub O, which is the permeability of free space, times the cross product E cross B. Now you're not really responsible for using this, but it's worth noting once in your life. So this pointing vector generally gives the intensity and the direction of propagation of our electromagnetic wave. So what we're really interested in is not the pointing vector or this equation, but really we're interested in the actual representation of the electric and magnetic fields. Now, in general, we're going to note that all electromagnetic waves propagate through space-time at the speed of light. Now, the speed of light is kind of the speed limit of the universe, so we think in physics. And the speed of light, right, SOL, is given by a lowercase c. It comes from the Greek letter or Greek word celeritis. And that lowercase c represents the speed of light. It's equal to 299,792,458 meters per second. Oftentimes, we round this to 3.00 times 10 to the 8 meters per second, but I don't really care for that approximation simply because it's too fast. The exact speed of light is the speed limit of the universe, but 3.00 times 10 to the 8 will work. Just for funsies, an approximation for the speed of light in miles per second is about 186,000 miles per second. So light can go around the equator about 7.5 times every second if it were orbiting us around the equator, which it probably doesn't. Okay, so this is our electric component. And this is our magnetic component, as we noted above. And as you can see, the vertical and horizontal slats that I've drawn still kind of line up and hit each other at 90 degrees or orthogonally. And so as the electric wave propagates downward, the magnetic wave propagates into and out of the page. And they always are oscillating orthogonal or 90 degrees from each other, and the oscillations are always always 90 degrees separated from the direction of propagation, which is shown by the pointing vector. So I'm going to show you a couple other things. The wavelength of this electromagnetic wave can be drawn in a few places. This is one that shows one wavelength. Another identical but kind of different place would be there. Node to node, or antinode to antinode, sorry. Those represent the wavelength of the electromagnetic wave. And we know that the wavelength and the frequency of the electromagnetic wave always yield the speed of light. And we can show that with this equation. So c, the speed of light, is equal to the product of lambda times f, where lambda is the wavelength, and f is the frequency of the electromagnetic wave. And frequency is always related to the period of the wave, of course. It's the inverse, so f is always equal to 1 over period. So capital T is the period of the wave. So the speed of light is, again, a kind of a constant speed limit of our universe, and it's always given by these two properties of the electromagnetic wave. So this should hold true for anything that we see. Our next segment of lecture will be the second segment. It'll be on the electromagnetic spectrum. So stay tuned for that one.